Hello everyone, welcome to this second video of this solving exercises series. So today we're gonna solve everything on one video. I hope it's quick enough. So what we're gonna work first is on problem 28. I think it's going through steps A and D, it's enough for you to understand what's the spirit of this problem, and you should not have problems solving B and C, which are based essentially on A, and it's very math based. So this problem asks you to compute the effective or RMS value of some signals. So for the first one, maybe is very familiar, but I'm gonna go step by step. This is a very important result in AC systems, so let's make sure that everyone understands it. So the effective value, or for practical purposes, the RMS value, it's defined as 1 over the period, integral 1 over the period of the signal, which in this case is a current, square dt, and everything under square root. So probably you already know that the effective value of a sinusoidal wave, a pure sinusoidal wave, sine or cosine, it's gonna be its maximum value, in this case the maximum value I max over the square root of 2. That's a very well-known result. I don't know if you went through it in class, but I'm going to show you with this exercise how it works. So let's go through it. So 1 over t. So the period in this case would be 1 over the frequency, right? So 1 over 4, that would be 1 over 0.5, right? 0 to 0.5, which is 0.25 seconds. That's the period, okay, of that signal. Signal square, so that means 3 times sine of 3t square dt, and all of that in square root. Okay, so then what we have to do here is work out this signal. Then the 3 square, in this case 3 square, we can move it outside of the integral, so it's not messing up with us. And actually we can transform this. This is this whole thing is 4 essentially. So it's gonna be 4 times 3 square, which is 9. Let's keep it as 3 square, just to it's easier to explain. 25 sine square of 3t dt, and everything on the square root. So so now what we do here, it's use a trigonometric identity, very simple one. So that sine square, it's simply 3 square 0.25 1 over 2 times 1 minus cosine square of the double frequency of the original one. Sorry, I'm using 3t. I got confused. Let me fix that. It doesn't matter actually, but let's use the correct value. So this should be 4. This one should be 4. So double frequency, it's gonna be 8t, right? That's the trigonometric identity. Sine square of alpha, it's 1 over 2 times 1 minus cosine square of 2 alpha. That's essentially what we're trying to convey here. So that's pretty much it. Then we can separate the integral into 2, right? 4 times 3 square, and we're gonna have 2 integrals. Actually, the 1 over 2 can be moved out of here. 4 times 3 square over 2. I'm purposely not combining all those. 1 dt minus 0.25 cosine square of AT. And then the square root. So on this one, the easy result here comes with the cosine. So the cosine of this double frequency signal, the integral of that, it's going to be 0. And you should be familiar with this result based on your calculus classes. You take the integral over of a signal of double the period of the integration, and that it's going to give you 0. Essentially, you're going to have 2 periods, something like that, and we're integrating across this time interval, so the area under the curve cancel each other. So basically, we're going to have 0 as a result. You can do the actual calculation, and you're going to get there, but that's basically the explanation. So we get only with this part, we're going to get 4 times, sorry, the color, 4 times 3 square over 2, and then we get 0.25, which is 1/4, right? 1/4 minus 0. Essentially that, and everything is square root. That is going to give us, essentially we can cancel out this 4 with this 4, and then we get the square root of 3 square, which is 3, divided by, and the denominator, the square root of 2. So 3, especially that 3 comes from the maximum value of that sinusoidal wave. So that's kind of the connection. Probably you went through this, but this is a very, very, very important result. Never forget that the relationship between the maximum value and the RMS value is 1 over square root of 2. That's the constant. That comes from this simple analysis. So you can use this result to solve part B and C, and it should be quite easy. Okay, now let's move on to a more developed problem, which is part D. What is happening here? Calculate the effective value of this signal, which is not sinusoidal or multiplication or sum of different sinusoidals. So we need to identify what's the essentially what's the period of this signal. We know that it's constant. From 0 to 1, it's constant equals 0. Then from 1 to 3, it's constant equal to 3, and that's basically 1 period, right? So it's essentially a function defined by intervals, right? So we can put it here actually. So we're saying that this function I of t is equal to 0 for t between 0 and 1, and it's equal to 2.82 milliamps for t in the interval from 1 to 3. And then it repeats itself. So the good thing about the effective value is that it makes sense for periodic signals. So we only have to take care of one period at a time. So in this case, the period is 3, right? And we have our function defined. So now we can apply the definition. So part B would be, okay, the IRMS, or the effective value, it's going to be 1 over the period, 3 seconds. The integral from 0 to 3 seconds. times the function. So now we can subdivide this. Let's do it right away. It's going to be integral from 0 to 1. The function is 0, right, on that interval, plus from 1 to 3, 2.82. It's a constant value, square dt. Simple enough. Then you solve this. This is, we know that is 0. And then we get 1/3. And here we get 2 times a, sorry, 2.82 square times 3 minus 2, sorry, 3 minus 1, and everything under the square root. So that's the result essentially. Now we only need to calculate. So I haven't calculated this one. So if we do this calculation, square root of 2.82 square times 3 minus 1, which is 2, divided by 3. And that is going to give us 2.30 milliamps. And it makes sense, right? And it makes sense in this case. It's going to be a value somewhere here. That's going to be the RMS value. You know, you should already know what the RMS means and why is it called the effective value. So whenever you're handling a problem like this, I recommend you to first analyze the waveform. Check when there is one period, then separate it into sections, and then you apply the definition. That's all you have to do. It's a periodic function that you can apply a definition to. That's simply the